So we have our cool creature model built here, and the next step will be to add some procedural animation, some kind of like wiggly flowing shapes moving through the tentacles. And later in the course, we will do some vellum deformable sims to really get some more nice simulated behavior on these tentacles. But it'll be really nice to, in the meantime, have some procedural animation there. And oftentimes, you will be doing procedural animation as sort of an effects task in some cases. And to do this animation, we're going to use VOPs, and that stands for Vex Operators. We've been mostly working in SOPs here, which is Surface Operators, and what Vex Operators do, VOPs, is it gives you a node-based way to essentially create Vex code. So if we go back to our environment portion of the scene, and if we take a look at this custom blend shape that we've done in Vex here, this Vex code that we've set up to do this custom blend shape could be done in a node-based setting in VOPs instead. So in a VOP network, you would read in these position values, and you would use one node to do this fit remapping, and that node would take inputs for the input value and the min and max and the new min and max, just a node accepting all these values as input, and then the output of that node could then be passed into another node that would do the same thing as our lerp command here, this linear interpolation. So this would be another node that's just accepting the two positions and the blend amount as node inputs. So pretty much anything you do in Vex could be done in VOPs, and vice versa. Pretty much anything in VOPs could be done in Vex. So it comes down to personal preference to some degree, which you like to use. Oftentimes, especially because I have a programming background, I like doing stuff like this in Vex. It's a lot easier for me to type this up rather than connect a whole bunch of nodes to do something like this custom blend shape. But whenever we're working with noises, I tend to like doing that stuff in VOPs. So let's go back to our creature here, and we're not going to apply the noise directly to the geometry. We're going to apply it to our tentacle curves. And I'll drop a null node down here to grab the curves and pull those to the side. Call this curves for anim. And then underneath this, we can drop in a point VOP, which will essentially, use nodes to generate Vex that will run over the points that this is reading in. So if you dive inside this point VOP here, actually let's put the display node on it first, and then dive inside. You can see you have these global inputs already set up. Gives you access to commonly used information like point position or velocity and age and life, and some of these things that are common outputs from particle systems. Color, normals, UVs, etc. We also have information on the current time and a whole bunch of other interesting stuff. So in order to generate some noise here and apply it to the output, we can just create any of a number of different noise VOPs here. You have a bunch to choose from. You can feel free to experiment with them if you'd like. Turbulent noise, anti-aliased noise, etc. For this, I'm just going to use a unified noise. And this unified noise a node essentially would operate the same thing as using a noise function in Vex. And of course you can set all the parameters on your noise however you would like, but all of these things can take inputs being wired into them as well. So the position reference that it'll use to determine the noise value is this pos down here. So we connect our point position from our globals into the position calculation for that noise. And by default, this unified noise is using a 3D input for the reference position and outputting a 1D noise value. But we want this to be a 3D noise because this is going to be used for X, Y, Z values. So let's change that to 3D input and 3D noise output. And then this noise here, if we connect that to the output position from our VOP network, this is going to take whatever those noise values are, and it'll overwrite the position with that noise value. So that's really just going to give us a mess down here. It's completely disregarding whatever the current point positions are, and just setting the position value equal to whatever this output is. So usually with this sort of thing, we don't want to use the raw noise output. We want to add that to the current position. So let's drop in an add SOP, or I should say an add VOP, connect the current P to that, and the unified noise in the second input, and then that sum will go into our P output. So when we do that, you can see we have the current position of the curve with these noise values being added to it. Now we can, of course, tweak the noise to our liking, and oftentimes with these XYZ parameters, I like to copy the X component for something like a frequency and paste relative reference into Y and Z. So that makes it easy for me to change the frequency of all the different axes just by changing one value here. So if we increase the frequency, can't really see too much visual difference, but that will give us much higher detail noise. And if we lower that down, then it'll be a much larger scale noise pattern. And this is pretty subtle right now. Those are pretty small waves running through those lines. So let's go to our final amplitude here. And once again, I will copy the X component, paste relative references into Y and Z, and we can turn up our final amplitude quite a bit. So if I set that to 5, then that gives us some larger flowy shapes. Now if we bypass this add and re-enable that, you can see that this isn't doing a very good job of keeping the lines in their original positions. It's kind of offsetting them in space overall. And this is because these noise values are only in the positive range. So instead of the noise pushing these lines in both directions, positively and negatively, it's only positive on every axis. So it kind of pushes everything in one direction like that. Sometimes it's helpful to see what the range is for your noise values, and one way that you can do that is to take this noise and put it into the color output in your VOP outputs here. And then if we exit out of our VOPnet and then zoom in on that, right click and check out the spreadsheet, then we can look at the values for the color that we're getting here. So you can see that right now these values run from around 0.8 or so up through about a value of 4. And this is because we used an amplitude of 5 on the noise. If you didn't increase the amplitude on this unified noise here, then those values would be a lot smaller, but still all in the positive range. And this unified noise has this output range setting that we can use to remap this. So let's set this to go from -1 to 1 in both Y and Z. And because this is still connected to color, you can see it's having that effect there as well. And for the X component, I actually don't want the noise to be pushing the points this way in X. I really only want the points on these lines to flow up and down, and then also side to side on the Z-axis here, like this. I don't really want them to kind of push back and forth in this direction. So for the output range, I'm going to set the min and max to 0 in X. And then we can also disconnect this from color because we don't really need that anymore. And now we can start to animate this. Right now, if we scroll through our timeline, then this isn't changing at all. But what we can do is modify the offset on our unified noise to do some animation here. So if we offset this in the X direction, you can see this will essentially push the noise through these tentacles in a pretty interesting way. And in order to set this offset value, we don't want to animate that directly. I suppose you could, but it's much better for things like this to use the time option on our global inputs here. And typically we'll want to put a multiplier on the time as well so that we can easily control how fast or slow this movement is happening. So let's create a multiply constant, and let's space these things out a little bit, and we'll take this time, put that into our multiply constant, and then we'll wire that into this offset here. And now this is working just fine to get some movement of this noise pattern flowing through the x-axis here, but this offset value is actually going to accept some x, y, and z values. So it looks like it's correctly interpreting this single time value and only using it for the x component. At least that's what it looks like based on what we're seeing in here, but I don't really trust it. Anytime that we have these parameters that are expecting vectors as input, I always like to convert them to vectors before using them. So instead of wiring this remapped time in directly, I'm going to use a float to vector, and we'll put this time scaled value into the first input here, and then connect that vector into the offset. And in this float to vector, you can see that it's just using values of 0 for the second and third components, so those will just get no offset on the noise, and this will ensure that this time remapped value is only being used for the x component of this offset. And it looked like the noise pattern was flowing a little bit too slowly, so on this multiplier, let's just crank that up a little bit. I'll try a value of 7, see what that looks like, and you can see that's a much more frenetic amount of noise flow. Now this is starting to look interesting, but all of these tentacles are getting pretty similar noise shapes applied, and it would look much nicer and more realistic if this noise was different for each tentacle. So one way that we can do that is to set a different attribute value on each tentacle curve, and then we'll use that in our offset computation. So we can use the connectivity SOP to get a different attribute value on each one of those curves. So just drop in the connectivity, and we can leave this as a point attribute, and then inside the point VOP here, we can bring in that new class attribute that we just created and use that in our offset. But we don't have that class attribute available in our standard set of global inputs. So we have to bring that in manually. So just type in bind, and this bind will read in attributes from our geometry, and in the name just type in the name of the attribute, which is class. And I should also point out there is a bind export, and this is useful if you want to create new attributes on the geometry from VOPs. So for example, we used the color to see the raw noise values before, but if you wanted to, you could use the bind export to create a new attribute instead. So let's perhaps take that noise value, put that into the input of our bind export. We'll call this noise test, And then if you jump out of the VOPNet, middle mouse on the point VOP, you can see it now has this noise test attribute. And this has the raw values of the noise in that attribute. But we don't really need that, so I'm just going to delete that bind export. And on this class here, we're going to use that for a Y offset on our noise here. Now, this is only going to give us a limited range of values. If we have 10 tentacles, I can't remember if that's how many we have here, and it's hard to see, but that will give us values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 on each tentacle. And that might be enough to give us some decent randomization. If we disconnect that, you can see it's certainly helping out a bit, but depending on the scale of the noise you're working with, that 0 to 9 value, if that's how many tentacles we have, is not necessarily going to be a large enough numerical range to be a meaningful offset. So just to be extra safe, we can do a multiply constant on this as well. And for this, we can just do something a little bit excessive, like multiply it by 100. So that'll give us offsets of 0 and 100, 200, 300, etc. to make sure that each of these sampled noise positions is very far apart for each of these tentacles. So now this is looking a bit more natural with that extra bit of variation, but it's still not going to line up with the body correctly. So if we put the template display just on the body portion, then you can see that this connection point is no longer working properly. So we need to remap this amplitude so that it's essentially 0 noise at the connection point, ramping up to more noise toward the ends. And now to do this ramp here, we can use the UVs that we've already set on the curves. So back inside our point VOP, we can use this UV input from our globals there. But this is going to give us, an X and a Y UV component. But we only want the first component of those UVs. So kind of similar to how we converted these floats to create a vector that we used for the offset, we're going to do the opposite with the UVs here. So the UVs are a 2D vector. So let's type in vector and we'll select the vector to float. So drop that in there, connect the UVs to that, and that will give us float values as the outputs for each component of those UVs. And now we can take that first component and use it as a multiplier on the noise that's getting added to these positions. So before we add the noise here, we'll insert a multiplication in there. So before we were using the multiply constant VOP, but in this case we want to use the multiply since we're using multiple inputs that we want multiplied together, not just a constant value. And the unified noise output will go into the first input, and our UV X component will go into the second. And because UVs are running from 0 to 1 along the length of these curves, you can see that gives us, essentially no deformation at the roots here, and full deformation toward the ends. So that's starting to look pretty cool. And we can do some more remapping of this UV value to help control the amplitude along the length of these curves. So let's use a fit range, that is. And this fit function will clamp the values to the min and max. You could also use the unclamped version if you'd like. You'll see the fit range unclamped will essentially extrapolate above and below the minimum values. So yeah, let's use that one actually. And if we drop that on our vector to float output here, that will connect this UVX component into the value input, and then we can just use these parameters to remap that UV value. So for the destination max, let's turn that up to 2, and that gives you more amplitude at the ends of those curves. And perhaps we don't want these deformations to happen, at the very beginning of the curves here. You might want the deformations to start just a little bit further back so that we get a more stable connection here. So you can just raise up this source minimum just a little bit. Like we just try a small value of 0.05. It looks like that should keep things a little bit more stable at the connection point here. So now we're all done sculpting this procedural noise here, and we can exit our point bop. And this is looking pretty cool, but we still need to apply this to our actual geometry. Now there could be multiple ways of doing this, but the way I decided to do it was to use a poly wire and then use that wire to deform the creature tentacles. So just create that poly wire and then connect that to the point bop. And it's okay for this one to be kind of low resolution in its radius here. It's only using 4 points, but we're only using this to deform the tentacles, so we don't need a ton of resolution on this. And we do need to make these thicker though, closer to the actual tentacle shapes. So one thing you could do is take the poly wire that we're using for these tentacle tubes. You could copy that wire radius, right click, copy parameter, and then we can relative reference that into the poly wires that we're using for our noise application. So I'll paste relative reference and that radius there. And now we have, this tube following those deformations that we've made. And in order to use this to point deform the tentacles, we're going to need a matching poly wire for the rest position. So I'll just copy this poly wire here, paste that, connect it to the connectivity, and when you're doing a point deform or a cloth deform, you need to make sure that the 2 inputs that you're using for the rest shape and deformed shape have exactly matching topology. And one thing that you can check to help ensure that is just to make sure that the point count is the same between those. So you can say this is 4,160 points, same as this. And that helps to make sure that it will deform the tentacles correctly. Now we don't want to deform this entire creature. We don't want to risk affecting the body here. So let's grab our cached out creature. So now I'll create a split SOP. Connect our cached out creature to our split SOP here. And on the split, I'm going to say at tentacle equals 0. And if we display that split, you'll see that's, setting aside the body for us there. And the second output of the split will be the tentacles only. And we still have the body displayed as our template display over here. So we can, turn that off. And we have our tentacles only, and we can do a point deform to apply that noise. So drop in the point deform, connect that null to the first input. Then the second input is the rest position, which will be, of course, this simple tube shape. And then the point VOP deformed poly wire into the third input here. And we're getting some decent deformations on these tentacles. And sometimes when point deforming, you'll get some bad deformations, kind of like this. You'll need to tweak the settings on this point deform a bit to fix that. And sometimes it can help to change the minimum and maximum number of points that are being used to deform any given point on the creature. But oftentimes, you'll just need to tweak the radius. This is probably the most important setting when point deforming. And you can see that as I increase this radius, then the capture gets a lot better, If you go overboard, then it starts to have some more problems, but it looked like a value of 1 was giving us some decent deformations of all of those tentacles. And you can also use a cloth capture to do some similar things, and that actually helps to visualize what these capture radiuses are really doing. So if you drop in a cloth capture, which you can then apply that captured deformation with a cloth deform. So you would essentially do this, capture the tentacles with the rest geometry as the second input, and you can see that this is actually showing you all of the influences of the captured geometry onto the geometry that you're deforming. And then this cloth capture goes into the cloth deform, which also needs the rest and deformer inputs. Although this cloth deform isn't working as nicely with these packed pieces of geometry, and typically I use point deform most of the time, but I just wanted to show you this as another option, and because this does help you visualize what these captured distances are actually doing, and you can kind of see how if you increase this cloth capture radius, then these influence areas from each of our rest tubes here, those influences start to reach other tentacles as well, which is why you have to be kind of careful when setting up these deformation radii, because you don't want this tentacle's motion to be affecting this one or this one. In any case, I'm not using the cloth version for this. We're just using the regular point deform. And with this animation now applied to the tentacles, we can merge that back in with the body here. And then, as usual, drop a null so that we can refer to this easily later. I'll call this out basic anim. And now we have this weird looking creature with some tentacle animation. And as I said, we're going to be doing something much better with Vellum later on, but this will give us some nice procedural animation to work with until we get to that Vellum point. And also, when doing effects work involving procedural animation, sometimes, things don't have to look perfect. You can see there's a lot of intersection between the tentacles because this is just a procedural animation without any collisions. But oftentimes, if in effects work, we're dealing with, 1,000 of these things at some sort of distance or all kind of moving around in a large swarm of them or something, then you don't necessarily need the level of accuracy that you would get from a simulation. And sometimes, just the quick procedural animation is totally fine, even if it's not quite as accurate.